Hello, in this in-class activity, we are going to learn how to calculate measures of dispersion and shape. We are going to use this simple data set to practice how to calculate these measures. Here, variance, standard deviation, and coefficient of variations are measures of dispersion. Skewness and ketosis are measures of shape. In our calculation, we also need to know the value of the mean, so it is a part of our calculation. In our calculations, we're going to use this table to make the demonstration very clear and organized. The first column contains data values. We find sum over these values to obtain 45. So this is the sum, and 45 divided by 7, which is the number of cases, will obtain the sample mean 6.4. Now, using this column, we calculate deviations. Deviations is the difference between data value and the sample mean. For the first case, 5 divided by 5 minus 6.4 give us negative 1.4. Okay, so 5 minus 6.4, we have a deviation which is a negative value. For the next case, 8 minus 6.4 give us 1.6 is a positive deviation. And the third case, again, is 5, so we have a negative 1.4. We do the same for all cases. We obtain deviations such as this. And there are positive deviations, there are negative deviations, and when you find the sum of these deviations, you obtain a sum of 0. The positive and the negative deviations are all cancelled out. Then next column, we use this next column to calculate squared deviation. For the first case, negative 1.4 squared give us 1.96. Every time when you find the square of a negative number, you have a positive number. 1.6 squared, you have 2.56. You do the same for all cases, you obtain squared deviations such as this. Then you can find the sum of squared deviations, and this is a number 19.72. When you come to calculate sample variance from the class reading material, you know that this is the formula we should use. On the top, numerator is the sum of squared deviations. So 19.72 goes to here. At the bottom, the denominator is n minus 1, the number of cases minus 1. So 7 minus 1 is 6. 19.72 divided by 6 is 3.29. So sample variance is 3.29. To calculate the sample standard deviation, this is the formula, which is simply the square root of sample variance. So after you obtain sample variance, you can simply find the square root of it to obtain sample standard deviation. In our case, sample variance is 3.29. the square root of 3.29 is 1.81. So the sample standard deviation is 1.81. Now we can calculate coefficient of variation, okay, which is sample standard deviation divided by the sample mean, 1.81 divided by 6.4. That gives us 0.283 times 100. We have 28.3. What does it mean? Coefficient of variation express the standard deviation in relation to the sample mean. We express this number as a percentage of sample mean. So we want to see how large the sample standard deviation in relation to sample mean as a percentage. In many cases, two datasets may have about the same sample standard deviation, but they may have very different sample mean. So when you come to find the ratio between the sample standard deviation and sample mean, you can really get a sense of relative to the sample mean, how large the sample standard deviation is. Let me use these two examples to illustrate the usefulness of coefficient of variation. Let's say that we have a few millionaires. They earn about the same income, about $1 million, about $1 million. But there are minor variations among them. There are a couple of dollars minor variations among them. But those couple of dollars variations among them divided by their total average income, $1 million, this percentage is very, very insignificant. In other words, the income variations among them is very, very small in relation to their average income. Now you have several workers who only earn the close to minimum wage, $10 per hour. Now there are some variations in income among them too, a couple of dollars differences among them. But now if you use the couple of dollars differences divided by the average hourly income, $10, this is a huge percentage. It's a huge percentage relative to, this income between the millionaires and these workers. The actual amount of variations of income is about the same, a couple of dollars. But when you divide these standard deviations by their average income, you can see that for the millionaires, that variation is very minor, but for these workers, that variation is very huge, at least 10% or 20%. So in terms of their average income. So I hope these examples to really help to illustrate the usefulness of the coefficient of variations to express standard deviation in relation to the average. Now we completed the calculation of measures of dispersion. Now let's go to practice to calculate measures of shape. First, let's calculate skewness. For skewness, we need to calculate cubed deviations. To calculate the cubed deviations, you can simply use deviation multiplied by the squared deviation. For the first case, negative 1.4 times 1.96. and give us negative 2.744. So that the negative sign carries over. For the second case, 1.6 times 2.56 give us 4.096. So we do the same for all cases that give us cubed deviations such as this for every single case. And we can also find the sum of cubed deviations. Now, this formula is what we use to calculate the skewness. Numerator is the sum of cubed deviations. So 14.792 goes to here or here. Okay. The denominator is n times the standard deviation raised to the third power, the cubed standard deviation for the sample. So here, 7 times 1.81 raised to the third power. Okay, and 1.81 cubed is 5.93. You complete this calculation, you obtain the value 0.36, and this is a measure of skewness. So skewness is 0.36. This is a value, is a positive value larger than 0, so we say that the distribution is positively skewed. This means that in the data set there are large outliers. Okay. So this is the skewness. Now let's calculate ketosis. For ketosis, we need to calculate deviations raised to the fourth power. This can be simply calculated by using the deviations multiplied by the cubed deviation. For the first case, negative 1.4 times negative 2.744, you obtain 3.8416, and you keep decimal to the third places, to the three decimal places, you obtain 3.842. Okay, for the first case. For the second case, 1.6 times 4.096, you have 6.554. Okay, and again you do this to all cases, and you obtain the deviations raised to the fourth power, such as this. Okay. Again, you can find the sum of deviations raised to the fourth power, and this formula give us the way to calculate ketosis. There are two parts in this formula. For the first part, on the numerator is the sum of deviations raised to the fourth power. So 74.174 goes to here. The bottom part, the denominator, is number of cases times sample standard deviations raised to the fourth power. So 1.81 raised to the fourth power is 10.733. Multiplied by 7, you complete the calculation of the first part, you obtain a value 0.99. But we're not done yet. The 0.99 minus 3 give us negative 2.01. This is the ketosis that we are looking for. since this is a negative number, we said that the distribution of this data set is flat. This means that we use a normal distribution as a reference. Later on, we're going to discuss the characteristics of normal distribution. This data set compared with a normal distribution, it is flat. So now this table lists all the values of measures we calculated in this in-class activity. Now, in our demonstrations, we use this table. As you can see, that within data values, there are repeated numbers. Okay. 5 occur 4 times, 8 occur 2 times. So during calculation, as you can see, that for those values that are the same, we did the same calculations numerous times. So for example, we did calculation for 5, same kind of calculations every time we repeat 4 times. And this is not necessary. For some data set, there are many repeated values. To avoid repeating calculations such as this, we design a data table like this. In this data table, the data values, the distinct data values occurs only once, but we have a column that tells us how many times this particular value occurred in the data set. For example, for 5, we record frequency 4, and for 8, the frequency is 2. So when you come to calculate the sum of squared deviations, you first find the deviation for each data value and you square them. Then you, in this column, you use squared deviation multiplied by the frequency. Then you find the sum, and this sum is the sum of squared deviations for the entire data set. And you use this number to calculate the sample variance. In the same way, when you come to calculate a cubed deviation for the entire data set, you first find the cubed deviation for each value. Then in this column, you multiply the cubed deviation by the frequency. Then you find a sum that would give you the summed cubed deviations for the entire data set, which is necessary when you come to calculate skewness. Finally, the same principle apply to the calculations of deviations raised to the 4th power. To basically, you first calculate deviations raised to the 4th power for each data value, then multiplied by the frequency. You find the sum over this column that should give you the sum of deviations raised to the 4th power for the entire data set, and bring that number to calculate ketosis. So at home, when you have time to use this table to do calculations as practice, the result should be exactly the same as those that you obtain in using the other table. I hope this helps. I see you next time. Goodbye.